David Pasley from NAVC, and I was once a RoboBoat team lead. So thing that I'm covering this year is basic autonomous navigation. This is the platform I competed with here. Basically autonomously navigating. So what exactly do I mean by basic autonomous navigation? Really what I mean is, maintaining a heading, waypoint following, station keeping, and anything that doesn't really require your robot to think very hard, like vision processing, mapping, path planning, or object classification, stuff like that. So the stuff that I'm really going to cover today, or again, is maintaining a heading and following waypoints. So by the time I get done with this, you should at least know what to Google. Wow. My phone's ringing. All clear. So where do we start? Well, we're going to start with thruster configurations and talk about motor mixing, and then we'll get into PID control and how do we tweak that and how do we set that up, and then navigating the waypoints. So let's get started here. These are the basic thruster configurations we've seen in past years at RoboBoat. There's rudder steering. We've got, I think, one team with that this year. We have azimuth thrusters, a single azimuth thruster. We have differential thrusters, vectored thrust, and Z-Drive, or dual azimuth thrusters. Surprisingly, we actually have at least 3 teams with that this year, although I think one of them has set it to just differential drive at the moment. So rudder steering is probably the easiest to do motor mixing on. That one, and azimuth thrusters, where basically you just have a thrust and a rudder angle that you need to command. And this basically boils down to mapping values into things that are usable by your servos or by your motor controllers. And that's also how azimuth thrusters working. So the plus side is the motor mixing is really easy. The downside is that it's a little bit mechanically complicated compared to, say, differential thrust or vectored thrust, where you have a static motor configuration. Speaking of differential thrust, this is probably the most common motor configuration that we run into here at RoboBoat and also at RobotX, because again, it's very easy to set this up. You strap a couple of say, trolling motors to the back of a WAM-V, and there you have a differential thruster configuration. The downside to this is that there's kind of less straightforward motor mixing. For instance, as you get going faster and you get closer to full thrust with a differential thruster setup, you lose the ability to turn quite as fast because you're actually using the differential between the 2 thruster speeds to carry out a turn. Then there's vectored thrust, which personally is my favorite. That's what we had on our boat in 2015, and it allows for holonomic control of your boat. I don't know if you guys have been through dynamics. I imagine our high school teams have not yet, but this basically boils down to general plane motion. You can spin, you can move laterally, you can move forward, and you can do all of these things at the same time if you really want to. The downside to this is it's pretty power hungry. Think quadcopter of the sea. It takes a lot of energy, but it gives you a lot of control. So it's fairly inefficient, but it's very easy to implement and easy to control. And then the last one is the Z-Drive, or the dual azimuth thrusters. We don't actually recommend that new teams try this configuration because it's a controls and optimization nightmare for undergrad students or high school students, for lack of a better way to put it. And the reason why, is I'll cover that later. But anyways, the Z-Drive is a very functional setup, and it allows you to get that holonomic motion in a lot of cases without losing the speed or the efficiency necessarily. So how do we control these motor configurations with a computer or a microcontroller? Servos can usually be commanded directly with a PWM signal from a microcontroller, or you can get a PWM controller. DC motors, you probably need to have a motor controller. Sometimes those can respond to PWM or an analog signal or maybe a serial signal. And brushless motors are typically driven with an electronic speed controller, or ESC, which is it typically responds to PWM signals, and then of course stepper motors require stepper drivers. So usually the output from a motion controller or a PID can't just be used directly by your motors, and that's where motor mixing comes in. It's what goes in between the PID controller and your motor drivers. So it converts motion controller outputs into motor commands. In the case of rudder and single azimuth thruster configurations, like I said before, this might be as simple as just converting one range of numbers to another. For instance, rudder angle to a PWM signal. And this is actually pretty simple. It just takes a little bit of math. In fact, you can do this approximately linearly. And there's an example here that we have in the slides. I'm not going to delve into the math on that. You can do that later. But basically, you can use a linear function to map, say, negative 50 degrees to 50 degrees to a pulse width of, say, 700 microseconds to 1500 microseconds. And if you're using like an Arduino, there's a function that'll do that for you. It's called map. And thruster mapping works very much the same way, except typically a thruster is going to have a dead band around the middle, so that on your RC controller, if it's maybe not exactly in the middle, you can still stop your thrusters there. So because of that, you'll usually set this up as a piecewise function, and there's an example of how you might be able to do that here. So you'll solve the linear function for, say, reverse and for forward, and then there will be a dead band in the middle. Stepper angle is, if you have a 360-degree stepper or a 360-degree azimuth thruster, it's more than just commanding an angle, because if you're moving from one angle to another, there is an optimal path there. So you'll have to solve, you'll have to find out which path is going to be the shorter path to your desired thruster angle. Vectored thrust, it basically turns into a 3D vector addition problem. So you'll have three different problems. This first slide covers a forward, reverse vectored thrust situation where you find out the sign of the values that you'll need to assign these motors in order to move forward or in reverse. Then there's the rotational, and you'll find out what the sign of these values need to be for a rotation. And you'll find out what the sign of these values need to be for lateral movement. And then what you can do in the end is add them all together, and then you might need to normalize these if they add up to over 100% of the values that you're mapping to. So this slide is an example of why we don't suggest that you use a Z-Drive or an azimuth thruster configuration. Basically, what you're looking at here is 12 different thruster configurations that could give you a 50% forward thrust. So if you look at this, you can see the vectors and how they're pointed and how they might add together, and you can have forward and reverse configurations for these motors. And depending on where you're at or where your thrusters are positioned at a given time, any one of these might be the most optimal for you in order to get that 50% forward thrust, as this example has. So moving on. We're going to go ahead and talk about controls now. And what we're looking at right here, I'm sure a lot of you maybe, who all's taken controls here? Okay, we have 2 students who have taken controls here, so you might recognize what this is. I'm not going to talk about this right now, but this is basically a detailed PID controller. So what exactly does PID do? We'll start with just purely proportional control. Proportional control will get your robot moving in the desired direction. Now, it might oscillate a little bit if there's not enough environmental dampening, but you can at least control your robot and get it going in the correct direction with proportional control. So the proportional control will act proportionately on the size of the error, and if there's any overshoot, then the system will oscillate. And that's where the differential part of the PID comes in. That's the D. Differential control will oscillate or will dampen those oscillations because it acts on the rate of change of the error. So basically, as this guy is turning, so if you're driving a car and you turn a corner, as you straighten out, you're going to slowly go back to straight. You're not just going to, you know, bring it back forward like that. So what the differential does is it slowly brings you to the heading that you want to do. But at the end, there might still be some steady state error. So you might not get exactly the heading that you're looking for, because the differential is not going to act on if your proportional isn't strong enough to act on the little bit of error there is, your differential is not going to act on it either, because it's not going to it's not going to, if the amount of error is not changing, then the differential is not going to touch that. And that's where the I component comes in. So the integral component acts on an accumulation of error. So the longer the error is there, the harder the system works to correct it. So that's what PID does. It helps you to efficiently and smoothly acquire a new heading or follow a particular heading. So what is PID again? So you have your measured state. This is not your actual state. It's just what your robot tells you your state is. And you have your desired state, and you create, from that you can figure out what the error is. You can figure out basically what needs to be corrected in order to be headed in your desired direction. So the proportional control is just going to be a coefficient multiplied times that error. Your integral component is actually going to keep an ongoing sum of that error and act on that proportionally with your I coefficient. And then your differential is going to it's going to subtract your previous error from your current error and figure out at what rate your error is changing, and then act proportionately on that number with this coefficient here. And then all these things are going to happen in parallel and then be summed together, and that's where you get your controller output. So how does it work? Again, you're going to calculate your error signal first, and then you're going to calculate your PID output, and then you'll make your move. That's what this guy is here, which results in your actual state, which you're then going to measure and do the whole thing again. It's a closed loop control system. And on this slide here, I know you can't really see it very well because of the because of lighting in here, but this is a basic PID algorithm, pseudocode, if you will. So how do we tweak this thing? You're going to start. There's a lot of different ways to skin this cat, but the way that I've found works best for me is the one that I'm presenting here. So you're going to start with purely proportional control, and it's helpful to start with your proportional coefficient at 1, and then and the other coefficient set to 0. So you're either going to reduce this thing or increase this thing until the system responds as quickly as you'd like it to. So if there's no overshoot, you can increase that coefficient, and if there's so much overshoot that the system looks like it's going out of control, then you should decrease it. Next, I adjust the differential coefficient of this thing. So you can increase that as long as there are oscillations. However, if it gets too high, then it'll act on it too early, and the system won't respond exactly as smooth as you'd like it to. So you can increase the differential coefficient as long as there are oscillations, and if it starts overcompensating before it reaches its target heading, then you'll want to decrease that coefficient. And lastly, if it's even necessary, you can increase your I coefficient in very small increments. It's usually very close to 0, if not 0. And basically, if you are uncomfortable with your steady state error, there's too much of it, then you'll need to increase your I component in order to get rid of that. So just increase it in very small increments, and if the system appears to if it appears to be becoming unstable, then you'll want to decrease that coefficient. So now that we've covered PID, we'll go ahead to the waypoint navigation. All you really need is your current location, your target location, and your current heading. You can get that with GPS alone, but it's not really recommended that you do that because GPS can be very finicky. So an example of why you wouldn't want to do that with only GPS. So say the error on your GPS sensor is 1 meter, which is fairly common. So here you are traveling along, and this is your actual heading, and your GPS sensor tells you that you're right here, which is within 1 meter of where you actually are. And then you make a move, and you haven't quite moved a meter yet, and then your GPS says that you're over here, which is still within a meter of where you are. And you calculate your heading, and it says you're going in almost exactly the opposite direction that you are, which will cause your platform to behave unexpectedly. Might do some spinning around or something like that. So with a GPS and compass, you can at least get a reliable heading to within a degree, and then with your target location and your current location, you can find that heading, and you can find the distance to that location very easily. If you want to keep the Earth's curvature in mind, there's something called the Haversian formula you can use, but you don't need that for this competition. So essentially you can tell your robot that the Earth is flat because Reed Canal Park is too small for the Earth's curvature to matter. So if you're navigating over the horizon or farther than that, that's when the Earth's curvature actually does start to matter. So before I go on from here, I want to talk about precision versus length. So you have these GPS coordinates, and they're given to you to some degree of precision. Usually, I think we're giving you 5 decimal points or something like that. And if you look at this scale that I got off of Wikipedia, great source, right? You can see that 5 decimal points will get you within 1 meter. This is usually about the accuracy of the sensor that you've got. But if you take it a step further and you have 6 degrees of precision or 6 decimal places, then you get to within about 10 centimeters, which is plenty precision or plenty accuracy for what we're doing here. So here's an example of using two GPS points without using Haversian, just a regular, just calculating this triangle here and figuring out your distance and also your heading, I think from west in here, but you can, if you use ATAN2, you can get this from east. And as you can see here, we're just calculating the difference in latitude, the difference in longitude, and then we're using trigonometry to find out what this distance is and what this angle is. Keep in mind the way that GPS coordinates are going to work is a little bit different. You can't just this difference in latitude and longitude because as one moves away from the equator, a degree of longitude is going to be multiplied by the cosine of your latitude in order to get a correct length out of it. And you can see that the calculation that I carry out here, Google agrees with it if you get the distance between these 2 points. The first point is the fountain out here, and the next point is here in the pavilion. So another thing that you need to keep in mind is the magnetic declination. So your compass is going to be using magnetic north, which is going to be different depending on what day it is and where you are in the world. And your GPS is going to be using your geographical north, which is not going to change very much. So your declination is kind of a conversion factor to get you between these 2 things so that you're working with the same units, the same north, essentially. And you can actually find the declination of a given date or location at this website that I have here in the slides. And so when I made this back in April, it was 6 degrees and 43 minutes west was the declination. So you'll correct for the declination by adding east or subtracting west declinations from your compass heading, or you do the opposite to the GPS heading, and then you have them using the same reference angle there. Now, another thing that you're going to have to worry about is wraparound. So when you're getting a compass heading, it's only going to go from, say, 0 to 360, or from negative 180 to 180. So if you're right around that 180 mark, your error might become huge all of a sudden. So as you go from, say, 179 degrees is your heading, and then negative 179 degrees is the next heading, suddenly you'll go from, say, 1 degree of error to 358 degrees of error. So this is actually pretty simple to fix, though, because if you think about it, you don't really need to make a turn that's larger than 180 degrees. So if your error is any greater than 180 degrees, then you probably need to subtract 360 from it, because you're looking in the wrong direction. And you do just the opposite if it's less than negative 180 degrees. So now we've got everything we need. We've got our current heading, we've got a heading to our target location, and we've got a distance to the target location. And this is basically, it's pseudocode. It shows how you can do GPS navigation from one point to another within one line of code. So while the distance is greater than your threshold, continue with your heading correction. So the reason that we use a threshold is because you have error in your GPS waypoint collection, and you have errors in your current GPS location. And so if you can only get within 1 meter, then you can set a threshold of 1 meter and get within that reliably, and then continue on to the next point. And that's pretty much it. So here's a recap of the algorithm there. You get your current location and heading. You calculate your desired heading and the distance to your desired location. You make a move using your PID, and you repeat that. You repeat 1 through 3 until you're within the threshold, and then you pick your next waypoint, and you repeat 1 through 5 until you're out of waypoints. Yeah, so that's all I've got for GPS navigation, and you'll see on the last slide a basic autonomy architecture. So what we went through is your motors and your actuators and your motor drivers, and we talk about motor mixing and everything here at a lower level, and we start getting into a low level of autonomy, which is basically just controls. And we talk about maintaining a heading and waypoint navigation. So I appreciate you guys for coming out again to see this lecture for a second time, and thank you for listening. So do you guys have any questions? Oh, anybody? Sure. No? All right. Have a good day.